Hey guys, so this is some stuff for 20 or chapter 20. And really, where we're headed is 20.4. We're going to go through a real basic synopsis of magnetism to help get you to a place where I'd really like to. There's a couple of highlights I'd like to hit that help make sense of some really important stuff. And so bear with me a little bit here, but we're going to try to cover a lot of stuff really quick to get to again, just one big idea. So the first thing we need to understand is that if we have a magnet, okay, it sets off a magnetic field. In other words, when you bring other magnets nearby, there's forces, there's pushes and pulls, and we can draw these what are called magnetic field lines to show us kind of the direction of magnetic flow. Okay, so if I were to bring another north close by, okay, another north pole from a magnet, this would show me which way it would get deflected. So we can see, and the more dense these lines are, there's going to be a lot of them right in here and a lot of them right out here coming in. Okay, the more densely packed they are, the stronger the magnetic field is. And that should make sense because if you pull a magnet way out over here, even if it's a north pole, it's getting pulled, but it's not getting pulled that much. And so, it's so. The closer we get, the more densely packed those lines are, the more they start to make a difference. And when we talk about a magnetic field, we're going to use a capital B. We usually put an arrow on it because it has a direction. Okay, so magnetic field. Ask me why we use B. I don't know. We just ran out of variables. But a magnetic field can be measured as a variable B. Its unit is a Tesla, and we use a capital T for that Tesla. Okay, so there's a couple baseline ideas that we have to have. Where our focus is going to be on creating uniform magnetic fields. When we put two magnets kind of close together, in between them, the lines start to straighten out. Out on the edges, they're still kind of curved, but right in here, we get pretty parallel lines right in the middle. And so the question that we really want to answer today is what happens when we take some sort of a positive charge, let's say a proton, and we send it zooming across that magnetic field. What happens to it? Well, we're going to find out that as it passes through this magnetic field B, perpendicular to that magnetic field in its direction, it's going to be affected and turned. Now, the first question might be, how much is it going to be turned? How big of a push or pull there is? And so the first thing we need to understand is we have what's called the magnetic field force, or the magnetic force on a charged particle. I'm a little tilted here. Bear with me a little bit. But the magnetic field, or FB, and guys, I know we used FB for buoyancy earlier in the year. We'll put a little arrow on it to give it a magnetic field direction. So FB is going to equal Q. It's actually cross B. We don't do cross products in this class. That's more of a calculus 2 or calculus 3 problem. So we're just going to write the equivalent B sine of theta. Now, a couple things. Q, that's just our normal charge. Okay. V is going to be velocity, not voltage. This has nothing to do with voltage right now, although the charge moving creates a voltage. And then, of course, we have magnetic field. Now, the sine of theta is the angle between B and V. So we can see that the velocity of this charged particle is 90 degrees from the magnetic field. That's going to happen a lot. And so you're going to notice just in the problems we do, because theta is going to be 90 degrees, we're going to end up saying that the sine of theta doesn't matter. So you'll see me use FB equals QVB. Okay, there's our formula. It's going to drive everything. And what this tells us is that if you have a charge that's either big or that's moving fast, it's going to have a big force. The faster it's moving, the bigger the force turns out to be, which is an interesting thing because if it's moving fast, it's not going to be in the magnetic field for very long, but it does have a high force. Coincidentally, if we increase the magnetic field, we're also going to see that same impact. If any one of these three things increases, we're going to see an increase in the force. Now, what we come to find out, and we're going to have to do a little bit of orientation, is that these things end up happening in 3 dimensions. We can't really do a 2-dimensional problem because of the way that the vectors cross and multiply to. So first thing that we're going to have to come to grips with is some directional agreement about directions, okay? And so can we agree that this is to the right? I think most everybody will say that's okay. This will be left. Whoop, there we go. This will be our up. This will be our down. Okay, and then this is where it gets a little bit tricky. How do we describe forward and backward? In other words, into the page and out of the page. If you think about an arrow, the traditional bow and arrow, if you were to look straight at the arrow, right? So imagine your eyes right here. You would see the tip of that arrow, and that's about it. So if we draw a dot like that, sometimes they're drawn with a circle around them, but this means out of page. In other words, towards you. Okay, so it's coming right towards you. And if you were to look back here at the back of the arrow, you would see some sort of a crosshairs as the arrow leaves you. Sometimes it's drawn with a circle, sometimes it's not. We're going to call this into page or away. Okay, so we have to have that agreement because when we draw these 3-dimensional interactions in 2 dimensions, we have to come to an agreement as to how exactly that's to be done. All right, so let's talk about this. This is the right-hand rule. Okay, you're going to need this in order to determine the actual direction. Okay, this is for finding the relationship between velocity, magnetic field, and force. Okay, these 3 different vectors are all going to be 90 degrees apart from each other. So not one of them is going to be parallel or perpendicular. Not one of them is going to be parallel, and none of them are going to match up. They're all going to end up being perpendicular. And so if you can imagine with my hand, I'm going to be way too close, but if something's headed, say, that way, to the right across your page, see how my thumb's extended at a 90-degree angle right here? I'm going to need to introduce one more right triangle, or one more right angle, and that's where we'll talk about coming out of the palm. I do it by just twisting my fingers. And so now I have 3. This is really hard to show on this camera, but you can see the direction that my hand originally went, the direction it turned to, that's 90 degrees, and then of course my thumb is coming out at another angle. So we're going to have to talk about these 3 things. Okay, the first thing we want to do is we start with fingers pointed in the direction of the velocity. I'm going to choose green for this. And you'll see why in the homework. There's a benefit to that. So let's say that I have a positively charged particle going to the right across my page. And it's going to enter into a magnetic field. Let's use blue for magnetic field. Okay, it's going to enter into a magnetic field. I'm going to call this bend. Okay, so I'm going to draw my magnetic field maybe going straight up the page. Okay, so there's my magnetic field B. Okay, as this guy comes into the magnetic field, it's at 90 degrees. I want to know which way the charged particle, which way this proton is going to bend. Is it going to bend up, down, right, left, in, or out of the page? So we use our right-hand rule to do this. The thumb is going to give us our force. So I need you to kind of imagine this with me, all right? So we're going to start with our hand in the our fingers are going to start in the direction of the velocity. See, my fingers are following the velocity. But I am going to curl or bend my fingers to match my magnetic field here in blue, which is up the page. You see I started to the right, I bend them to come to up the page. My thumb is pointing right at you, right? Jumping right out at you. You guys get that 3D effect? Okay. So my thumb is coming right back at the camera, which means that the force, okay, here in red, would be that single dot. coming right back at me. So this charged particle, if you can imagine, it's coming along, it hits this magnetic field, and then it starts to curl and come up towards the camera. It's being bent by the magnetic field. Okay, let me draw you a different example. It might be a little bit easier to see. I'm going to have, again, positive charge right here, headed to the right. But this time, I'm going to let my magnetic field be into the page. That's what the X's represent. Okay. So you can imagine I'm coming in right here, and then there's a magnetic field going straight down into the page. And I want to know, where is my charged particle going to bend to? Well, if we follow the rules, start with your fingers in the direction of the velocity. But to curl my fingers down into the page, I'm going to have to turn my hand palm down. So my fingers can now curl into the page, right? They were across the page. Now they're curled into the page with the X's. And you can see my thumb is pointed up the page. So I can say up would be the direction of the force. The force on this particle is going to be upward. Now, so long as this particle stays in this magnetic field, that means it's going to get deflected. Because as it changes direction, that magnetic field is going to change. The further I go into this curve, this magnetic field is going to turn with me. It's going to continue to turn and always point inward on that curve. Okay, that should have been there. But it's going to continue to curve the direction because it's being pushed upward. Once we know which way it starts to curve, it's just going to follow that curve until it exits. And out here, it would exit and go that direction. Okay, so that's a way that we can turn these things. This is extremely important because this is at the heart of how we use linear accelerators and X-ray and man-made radiation to treat cancer. We use this, and we have to know, are we able to hit our target? How many degrees do we need this to turn? Where do we want to aim? These are really important questions. I've been in the St. Luke's Tumor Institute where they do cancer treatment, and I've seen the devices they use, and they do this exact kind of calculation to hit a target of those cancer cells. So it's way cool stuff. It's very, very applicable. Let's talk about your homework problems and kind of get you set up with how we're going to use this information to help us. Oh, by the way, just down here, if you need some more practice with the right-hand rule, here's a cool video. It's about 8-9 minutes long, but he goes through and talks about all these different setups. Well, what about here? What about there? And you'll see some of these in our homework as well. I'm going to jump into chapter 20, just looking here at 9 through 14 is this first part. And so looking at the beginning of this, number 9 and even question number 10 are pretty similar. They're even very similar to 13 and 14. So we're going to talk about those here in just a minute. First, I want to talk about our simple right-hand rule problems. Okay, if we look at 11 and 12, okay, we're going to be using the right-hand rule to just determine some directions. Okay, and you see them right here, left, left, up, in, none, and down. Okay, those are our solutions for this. A couple things. All right, let's look at this first one. Remember, green we used for our velocity. That's where our fingers start. So on part A, do this with me. Point your fingers straight at your nose, okay? With your right hand. Remember, this is a right hand rule. So point it right at your nose, okay? That means it's coming out of the page at you. The next thing you're going to do is you're going to bend your fingers in the direction of the blue magnetic field, which is down. Your fingers are pointing at your nose. You turn the fingers down. Your thumb, if you extend it while holding your hand in that position, should point to your right. Hopefully you guys all have that. Unfortunately, that's wrong. The reason it's wrong is because of one little thing right here. Negative charge. Being a negative charge means that it is the opposite. So once you do your right hand rule, you're going to flip the direction, exactly opposite, and that's your answer. Looking at question number, let's do F right here. Fingers are to the left initially. I need to curl my fingers in the direction of the blue B, which is straight out of the page at me. So my hand is pointing to the left. I curl my fingers towards me. My thumb should be pointing straight up. And because it's a negative charge, I reverse that and go down. So that's question number 11. That's how you'll do those. Question 12 is almost identical, except we are going to use positive particle, so that's good. We get to go back to just positive. And the second thing is they're skipping the magnetic field. They're asking us, hey, where's the blue arrow? Oh, by the way, the whole time we were finding the red force, the direction of the force. That's what our thumb does. Here, they tell us where our thumb points. They tell us where our fingers have to start, but they don't tell us where the bend is. Let's take a look at option B right here. If you start with your fingers out to the right, okay? So you extend your hand out there to the right, but you have to turn your hand so that your thumb is naturally pointing upward. That should turn your palm towards the computer, if I'm on the same page as you. Now, I need to know which way does now that I've got my fingers initially in the velocity of green, my thumb in the direction of red, the magnetic field is the direction that my fingers can naturally curl to. Just turn them 90 degrees. They should be pointed into the computer screen. That's where option B's answer is, into the page. Okay. So that's how we use the right-hand rule. And yeah, if we were ever to get back into class, then that's a beautiful test question. I love seeing 30 kids sitting in a room all using their hand to kind of in three dimensions, trying to twist it and bend it to get things to line up. Again, that video is a really good video for just walking you through the different options with the right-hand rule and how they different things interact. So those are your two right-hand rule problems, basically. I think 11 also asks for the right-hand rule, so kind of be aware of that. 13 might also, although I think it's less important. There. So number 9 and 10, we're going to be asked about the motion of charged particles. And so what I want to do is jump back over. I'm going to have to jump back over to our paper over here on the side. Look at another example. So let's imagine we've got a magnetic field here. Make it kind of big. Get a little bit of an effect here. It's a nice uniform magnetic field. Okay. Let's go back to the question. Okay, we've got a positive particle. Our little positive particle. It's 2e, but it's positive. So that's 2 times the charge of an electron. They give us the mass of it, and it's sent out at a speed with 1.6 times 10 to the 7th. That's actually pretty close to the speed of light. It's not quite there, but it's pretty close. And the question is, what's the magnetic field strength in order to cause it to turn into a 0.25 meter radius path? All right, so first off, right-hand rule here, positive particle to the right, down into the page, my thumb's pointing up, which means that this guy is going to follow a circular path that way, as it's going to get bent while it goes through there. Now, let's assume that the radius of curvature R is 0.25 meters. So the question is, how big is our magnetic field in order to produce that? Well, if we talk about what we learned today, or what we were talking about today, you know that the force on a charged particle that causes this rotation is equal to QVB. All right, now here's our unknown. Our big unknown is that B that we're after. We know the velocity, that's given. We know the charge is 2 times E. We even know which direction it's going to turn. But how in the heck is the force supposed to be related to its radius of curvature? Well, if we can remember way back in like chapter 5, way back in first semester, we learned that the force required to create a circle, okay, the radial force for a circle, was always equal to mv squared over r. If we will allow our magnetic force to equal the centripetal force, those two equations set equal to each other should allow us to solve for B. This is a really common approach to solving problems like this. And in fact, if you look at question number 10, number 10 is much easier, but you do have to come up with the direction, which is a right-hand rule. Number 10 is just a F equals QVB. Really straightforward problem. But on question 13, it says an electron projected vertically upward, okay? Describe the electron's path in this field. What we're looking for is the radius of curvature, which means you're going to have to come back to this same equation where QVB equals mv squared over r. That's going to be a baseline that you're going to use on question 13 as well. Last question, number 14, there are a couple of hiccups that we need to talk about, and then it becomes a similar, easy problem to solve. First, 5 mega electron volts. This is its kinetic energy. It's a proton. It's entering a magnetic field. What's the radius of its path? So this is not the force. They never gave us the force. So QVB doesn't really look like it's part of this, at least not initially. But they did give us the kinetic energy. So the first thing you're going to have to do on number 14, this is just a unit issue. They have 50 mega electron volts. I've got to turn this into joules. The way we do that is just times by the charge of an electron, 1.602 e negative 19. This will create joules, okay? So then you have your energy. Well, we know that that number of joules is equal to the kinetic energy, which is 1/2 mv squared. Now, they told us it's a proton. The mass of a proton is given in your textbook way up here in the useful charts information. You can see it right there, okay? 1.67 e negative 27. So I'll let you dig that out when you're using it. But coming back in here, okay, we know that there's a charge. We know the mass. We don't have the velocity though. So this is kind of weird because we're missing a lot of information. But here's the good news. As we come back here, because I know the mass and I know the energy, I should be able to solve for the velocity. Okay? If you solve this problem for the velocity, the next thing that you could do is say what F equals QV is. Because they did give us the magnetic field. They did, now we have the velocity, and we already knew the charge was the charge of a proton. Well, we know that that is also going to be equal to mv squared over r. And there is the prize. Using, again, mass and velocity, you should be able to solve this. If you want to rewrite this formula, for instance, this v would cancel one of the v's in the v squared. If you want to rewrite it a little bit to make it easy to solve because you'll use it several times, go for it, no problem. At this point, if you have questions, you're just going to need to sort of discuss it with me during office hours. Come have a chat about specific questions. Get online with your friends, talk to each other. That's the best thing you can do is dialogue and collaborate. Good luck, and we'll see you in class.